Let R be the region in the xy plane between the curves y equals x cubed and y equals the square root of x. And we're going to find the volume of the solid that lies beneath the plane, z equals 1 minus x over 2 minus y over 2, colored in orange, and above R. So first we'll visualize what part of the plane lies directly above the region R, and then we'll get rid of the parts of the plane in orange that we don't need anymore. Then we'll fill in the sides, and that'll give us a good idea of what the actual shape is that we want to obtain the volume of. In this video, we're going to set up a double integral that will compute the volume, and we're going to walk through two ways to rewrite the double integral as an iterated integral. First, with respect to y, then with respect to x, and then vice versa, with respect to x and with respect to y. And the difference between the two orders has to do with how we take cross sections of our two-dimensional area R. So if I think about the two-dimensional area R here, I could think about taking vertical cross sections. And the way I'm thinking about that is it's the same curve on the top and the same curve on the bottom as I move through the region. So here x is the independent variable. So when we set up our double integral in a moment, we're going to rewrite this double integral as an iterated integral where we integrate y first and then x. Now you just do your typical integration rules. And we're going very quickly through our integration rules, but this last formula down here calculates the area of this green trapezoidal shape that you see. And what the integral does is it adds up all these areas as I move through the shape. And so the sum of these cross-sectional areas is what we take the volume to be. And when you take the sum of these cross-sectional areas, when you actually do your antiderivative of that function that you obtain, you get about 0.23. So that would be about the volume of this shape right here. Now what we're going to do is we're going to rewrite the double integral as an iterated integral with respect to x and then y. So we're going to take horizontal cross sections, and that means that we're going to treat y as the independent variable. And when we take horizontal cross sections, we want to have it be so that the same curve is always on the left and the same curve is always on the right as I move throughout this region. If you can do that, then it's possible to calculate the volume via these horizontal cross sections. We take our double integral and we rewrite it with respect to x first and with respect to y. We do our typical anti-differentiation rules where we treat x as the variable and y as constant. And so after that, we obtain an integral that just has y as the variable. And that formula that you're integrating, again, that formula calculates the cross-sectional area that you see. And you can visualize the integral as adding each of these cross-sectional trapezoids up. And you get 0.23.